Welcome back to this series on archival data research and accounting that I've been working through with you all for the last, I don't know how many videos we've done at this point, but we're currently on replicating the influential paper from Ray Ball and Philip Brown, published in 1968. And it's a paper that new accounting doctoral students and even finance doctoral students learn about, and the accounting students definitely have to read the paper, understand what's going on in it, and you may or may not have to replicate it in your seminars that you have as an accounting doctoral student. But if you do have to replicate it, well, these videos will prove very, very helpful, at least if you're going to use Matlab to do the replication. But let's see where we left off last time. I believe, go ahead and bring a paper in. I believe last time in the last video we had computed the unexpected earnings using equations 1 and 2 in the paper. So now we have the unexpected earnings for firm I in period T, or if you want to use their subscript J in period T. And now we need to, and we also have, so we have the abnormal, we've computed this right here over our sample time period, which is the difference between what we expect earnings to be and that right there. There should be a hat, like I said before, above the I up here. So this and this are the same. Our expectation for what the earnings should be, or the change in earnings should be, we're using changes in earnings. That's what makes this a little bit trickier than just regular earnings. Earnings itself is not stationary as a time series, and that's why the authors take the first difference in earnings, the change in earnings, so that it's a stationary time series, and usual assumptions are satisfied in terms of linear regression, OLS assumptions. That's why they take the change. But our estimate for the change in earnings is given by this model up here, and we went through that in the last video. You run the regression up here in equation 1, get the estimated parameters A1 hat and A2 hat. You plug those in with the actual market change in market earnings, and you get the expected change in firm J's earnings in period T. Subtract that from the actual change in firm J's earnings in period T, and that gives you the unexpected change in firm J's earnings in period T, or the abnormal, this right here. So we computed that in the last video. We also, in the last video, I think we left off with replicating table 3, which were the earnings announcement dates. And we compared that to table 3 in this paper. But in this video, we need to go to the next stage of the replication, which is replicating the part in the paper where they estimate the unexpected market reaction. We're going to use the sign of this, right? The sign of the unexpected earnings. If it's positive, we're going to say that when the firm announced earnings, it was a positive announcement. It was a positive surprise. And if this is the sign of this is negative, then it was a negative surprise. And then we're looking to see what happens to the market reaction in the positive surprise announcements and the negative surprise announcements. And we're hoping to replicate figure 1, the famous figure 1 in this paper, which shows that, if we go back down here, for the positive earnings announcements, month 0 is when they announced. These lines up here are the positive earnings announcement case. Variable 1 is where we use just regular net income for earnings. Variable 2, I think, is earnings per share for earnings. And then variable 3, I can't remember. We're doing both variables 1 and 2 in our paper. But these are the positive announcement cases where the unexpected earnings, the sign of the unexpected earnings, or the sign of the abnormal earnings, or the sign of U hat JT is positive. The sign of U hat JT is positive. then this plots out the market reaction, the unexpected returns for those particular firms. 12 months leading up to the announcement date, and then 6 months after the announcement date. When the sign of the unexpected earnings was negative, then this plots out for those firms the unexpected returns for those firms leading up to their earnings announcement dates and then afterward. And you can see the drift, the post-earnings announcement drift. Even after the earnings announcement, prices continue to drift downward in the negative surprise case, upward in the positive surprise case. And then interestingly, prices are already drifting upward in the positive surprise case and already drifting downward in the negative surprise case, even before earnings are announced, which is evidence that prices are somewhat pretty efficient, and the market knows in advance what's going to happen to some extent. But prices aren't completely efficient, because if they were, then as soon as they announced, prices would immediately reflect all available public information, and they shouldn't continue to drift downward in the negative case and upward in the positive case. So again, this is an anomaly that was documented in 1968, and to this day, we still don't know why. Why do prices keep going up? Why do they keep going down after the earnings announcements? Positive surprise case, negative surprise case. Post-earnings announcement drift, PED. So let's go to the next part of the replication, which is we need to compute the unexpected returns, or the unexpected market reaction. So the impact of market-wide information on the monthly rate of return, I'm on page 162 of the paper. The impact of market-wide information on the monthly rate of return from investing $1 in the stock of firm J may be estimated by its predicted value from the linear regression of the monthly price relatives of firm J's common stock on a market index of returns. And in the footnote down here, they talk about, well, here's the definition of a monthly price relative. It's just closing price plus dividends for the period divided by opening price. But that you can show mathematically is equivalent to the monthly rate of return plus 1. And then down here, they say that they're citing and they're using Fama et al. 1967, their result, where they conclude that regressing a given security's returns on the overall market return over a period of time is a satisfactory method for abstracting from the effects of general market conditions on the monthly rates of return of individual securities. In arriving at that conclusion, they found that scatter diagrams for the returns on individual securities vis-a-vis the market return support very well the regression assumptions of linearity, homoscedasticity, and serial independence. And so since this study and other studies that found similar results, this particular market model, and this is just known as the one-factor market model, has been done, where we regress the return of a given firm. This is the monthly price relative of a firm minus 1. Remember, the monthly price relative is the monthly rate of return for that firm plus 1. So when we subtract 1, we're just left with the monthly rate of return. So the left-hand side is the rate of return for the firm in a given month, and in the right-hand side, we have the rate of return for the market for that month. And so this is your intercept, and this is your classic beta coefficient. But in this paper, they've labeled them B1 hat and B2 hat. But this is beta right here. We're trying to estimate beta and the intercept, but we're gonna call them B1 hat and B2 hat. We want to estimate, and then we can go and do the same thing that we did with the unexpected earnings. By they don't actually have an equation in here, but once we use this equation to estimate B1 hat and B2 hat, we can plug those in with the actual market return in a given month. That gives us the expected return for that firm in that month. And then from that, we can subtract the actual rate of return for that firm in that month to get the unexpected rate of return for that firm in that month. Then for each month, we can compute the unexpected rate of return or the market reaction. Or the unexpected rate of return, let me say that. Now, since this time, since this 1968, 67, there have been expansions of the Fama-French model. So Fama-French themselves in the 90s expanded their model to include two other factors. So we have 3 beta coefficients we would be estimating, well, 4 including the intercept. Instead of it, so the market return is one of the factors. The rate of return on a portfolio of big stocks minus the rate of return on a portfolio of small stocks. Small stocks minus big stocks. So SMB, the SMB factor. That would be in the model. And then another factor would be the rate of return on high value stocks minus the rate of return on low value stocks, or high growth stocks minus the rate of return on low growth stocks, is the third factor. The Fama-French 3-factor model is what it's commonly referred to. The market factor, the SMB factor, and the HML factor. And then even after that, there was another factor that's been added. Mark Carhart in the mid-90s found that there's a portfolio that you can construct based on prior returns using momentum. So stocks whose prior returns in the past, 24 months were really high. We can construct a portfolio of stocks where we long those stocks whose rate of returns in the prior 24 months were exceeded a certain threshold, and we short those stocks whose rate of returns were less than a certain threshold. And the rate of return on that portfolio, called the momentum portfolio, is also shown by Mark Carhart, Journal of Finance, I believe, 1997. The rate of return on that momentum portfolio has been shown when you add that to the model as a fourth factor. It can explain the R squared of that regression is statistically higher than the R squared of just the Fama-French 3 factors. And then since Carhart's fourth factor, there's been a Fama-French 5-factor model and so forth. So there's a lot of stuff that has been done since the 1960s. But at that time, this is the market model they had. They used the market rate of return, regressed the individual securities rate of return on that market rate of return, and got an estimate of the intercept and the coefficient, and then used that to form the expectation for what the rate of return should be in a given month. So that's what we're going to do. So let's go back to our code. We left off with replicating table 3. If you remember in the previous video, go watch the previous video if you haven't. Earlier in our code, we had finished computing the unexpected earnings right here, and we put that in a matrix called UE. So what we're going to do now is we need the year, month. All we need is the year, month of the report date of fourth quarter earnings. Let me go ahead and run this first in this video. This is what we had where we left off last time. Oh, I need to change. My default folder. The data is located. Boom. Change my path there. Let's go ahead and run this and get to where we left off last time. Then we'll continue. Not exactly sure how long this will take, but maybe we'll cut this part out of the video. All right. So we're done. The code ran, and we have our unexpected earnings where we left off last time. We had computed the unexpected earnings. Let's see what we had. So in column 4, we have unexpected net income. And in column 5, we have our unexpected earnings per share, our EPS variable, because we're using two variables to measure earnings, regular earnings and then earnings per share, just like the paper. So if that's where we left off last time. So in our unexpected earnings matrix, in our date column, all we really need to replicate the paper is the year and the month. We don't need the actual day. So we're just going to get the year and month for column 3. We're just going to convert column 3 to just the year and the month. So let's go ahead and redefine UE as just first column. First two columns are going to be what they were. Third column, though, is going to be the current third column divided by 100. And then we'll take the floor of that using our floor function. And we've done this multiple times in previous videos. So what that will do is when you divide this number by 100, you'll be left with 198303.21. You just move the decimal place 2 places to the left. Then when you take the floor of that number, it's everything to the left of the decimal place. It rounds to the nearest integer downward always. So, and then the last two columns will just be the current last two columns. So as far as a note goes to ourselves, only need year, month of report date of 4th quarter earnings. All right. Now, earlier in, I think the first video, we had taken the, we had brought the returns in, market returns in, you know, as a table way here. And then we had removed, I believe we had already removed stocks that didn't have share codes 10 or 11. We had converted the date variable to only year and month. So does the date, is it already year and month? Somehow we're back to we have day again. Oh, we converted the date variable to a double array from a table, from a date time to a double array. So you see here in the table, it was a date time array. Oh, it's a double now. Oh, because we converted it right here with this line of code. So this actually converts the date variable to double data type. Change that part in the comments section. But we didn't yet get, and then we converted the whole table to right here in this line to a double array for faster computation. But still, the date variable is the full YYYYMMDD, right, format with the day. So now what we want to do is go ahead and just get the year and month for that. So we're going to start using the returns data, which is in the crisp double array. So we're going to let crisp just equal, I mean, we can do the same thing we did here. Only crisp, it has 5 columns as well. So it's basically, we can just copy and paste from up here. And just change this to crisp. So I believe it has 5 columns as well. Column 3 is the date column. We want columns 1 and 2 to stay the same, 4 and 5 to stay the same. But it's column 3. We want to just take get the month and the year. Column 1 is the perm no. Column 2 is the GV key. And then column 3 is the date. Column 4 is the rate of return, the monthly rate of return for that particular firm for that particular month. And column 5 is the market rate of return for that particular month of that particular year. That's in column 5. And we can verify. So February of 1986, that's the market rate of return. February of 1986, it's a different firm. Still, market rate of return is the same. Column 5 is the market rate of return. How did we get the GV key? I think we did that earlier. Yeah, we did that in an earlier video where we used this linking table. And because originally our market data only has perm no, it doesn't have GV key. It's CRISP just has perm number, it doesn't have GV key. But we did that in the first video where we already linked the GV key to the perm no. So go ahead and run this line of code. So now we got the column 3 is just the year and the month. And then for UE, column 3, oh, I didn't run that code yet. I need to run this. For UE, column 3 is just the year and the month. Because remember in figure 1, we don't care about the actual day. We just care about the month. Month relative to annual report announcement date. So whatever month fourth quarter earnings were announced, they'll be announced in the next year. Fourth quarter of a given year comes, and then earnings for that fourth quarter are announced next year. And that's what table 3 was showing, like on what day, when were those earnings announced? There was a distribution. Pretty much by the end of March, all the firms that announced earnings usually are close to most of them. Anyway, we need the month. We don't need the day. We don't care about the day. So let's go back to this. All right. All right, now let's go ahead and sort the rows using the sort rows function by column 1 and then by column 3. Now it's already sorted by column 1 and then by column 3. So we sort rows by perm no, then year dash month in ascending order. It already is, but just to be sure. But by default in CRISP, the data always comes in sorted first by perm no, which is the identifying variable, the unique identifier in perm no, in CRISP. It's sorted by that, and then it's sorted by date. But we'll do it just in case it wasn't already, because if it wasn't already and you didn't do this step, then the rest of what we're going to do doesn't work. Let's get the unique firms that we're dealing with. So based on the perm no, the unique perm nos. Which technically, the GV key, which is in column 2, tells us which firm it is. And the perm no in column 1 tells us which security it is. A given firm can have multiple securities. Could have common stock class A, that would be one perm no. Common stock class B, that'd be a different perm no for the same firm. So I guess technically I should say get unique securities. Get unique common stocks. You know, they're all common stocks because we already made sure of that earlier. And then what we want to do is we want to delete firms which don't have at least M months of returns data. over the sample time period. And we're going to see page 167 along with the last sentence of paragraph 3 on page 163. And we're going to let m equal 100 because that's what they did in the paper. This is the minimum number of monthly returns desired for each stock. So if you follow their paper carefully, you realize that they impose very stringent constraints for a given firm to end up in their final sample. And the constraints they impose, like for example, we read earlier, go to page, we did this in last video, if you go to page 167 where they talk about their data, or let's see, where do they, the inclusion criteria, right here, remember we're sure now our sample time period is not the same as theirs because we don't have data back to when they started. They go from 46 to 66. We go from 1970 through 1990, a 20-year sample time period. We try to be the same in that regard, 20 years, just like theirs is 20 years. But they want to make sure that they have at least 10 observations of earnings for each firm. 10 years of annual earnings for each firm. And so that already biases against any new firms coming into the market that won't have 10 years of observations yet. These firms that have lasted for at least 10 years are probably bigger. So already, and they acknowledge those limitations in terms of overall generalizability of their results. They acknowledge that as a limitation later in the paper, but their constraints are pretty stringent. And you'll see we'll be left with a kind of a small sample of observations that satisfy all these criteria. Another criteria is that they have to have it. So to estimate this regression equation that we're trying to estimate here, regression equation 3, where we regress the return for firm J in month M on the return for the market in month M, we can't estimate B1 hat and B2 hat for firm J unless firm J has at least 100 monthly observations over the total sample time period. And they talk about that, what did I say, last sentence on page, last sentence of paragraph 3 on page 163. So no, that's not what I want. Where's page 167? Where do we find this out that it's got to be 100? I think it tells us on page. Oh, right here. Yeah, I was right there. So price data available on CRISP tapes for at least 100 months. Over the whole sample time period. So what we're going to do is delete firms, or securities really I should say, which don't have at least M months of returns data over the sample time period. I don't think this, I think just that is correct in terms of the comment. So we've already created, let's run the firms. This, we didn't run, yeah, we ran this. We already have our unique firms. Run it again, make sure we did it right up here. We already have our unique securities. Here are the unique permnos for all of our sample data. Here's our sample data again. And for each of those perm nodes, we want to make sure that they have at least 100 observations. And one thing that's, it's kind of, this is going to be kind of hard to explain, but one thing that wasn't clear to me in their paper, but they would have made it clear if, so all it says is they have to have at least 100 observations. What it didn't say is for a given firm who we have their unexpected earnings for at least 10 years, right? What does this say? You're assured of at least 10 observations. So their sample time period is 46 through 66, but they limit their analysis to the 9 fiscal years 57 through 65. By beginning the analysis in 57, we are assured of at least 10 observations. So firms have earnings observations years 46 through 50. January through June 66. So that firms have earnings from in 46. They have annual earnings observations in 1946 through 1955. That would be 10 years, right? Then why do they begin in 1957? They should begin in 1956. I'm a little confused there. Because 1946 through 1955 is 10. We give 10 observations for each firm. Oh no, that would only get, would that be 10? 46, 47, 48, 49, 50, 51, 52, 53, 54. 55, that's 10. So I don't know why that didn't say 1956 there. But anyway, what it doesn't say is that the 100 monthly returns for the firm have to be before the earnings were announced, which should be the case because you should use the prior monthly returns to estimate the market model. You shouldn't get to have the benefit of looking ahead. It's like look ahead bias, and use monthly returns in the future past when the earnings are going to be announced to estimate the market expected, use it to get the estimates of the betas, right? The intercept and the beta coefficient used to estimate the expected market return for some time prior to that in the past. You shouldn't be able to do that, but that's what they did in this paper. And if they didn't do that, then it would have even more severely limited their sample. But if that makes sense. So all we need to do then, it does make it easier to replicate though. It's easier to code. We just have to make sure that for each security that's in our data, for each unique security, like here's one with perm no 10000. That's the first one here. For each security, we need to make sure it has at least 100 observations. And it did not say that they had to be consecutive observations, consecutive months. There could be some gaps. It didn't say they had to be consecutive. So with that in mind, let's write a for loop where I equals 1, increment by 1, all the way up to the number of securities we have, which is in our firms array. And so it's the size of our firms array in the rows direction, 10301. So we're going to increment through that. So if the sum of wherever you can find firms I1 equal to crisp all rows column 1, if that sum is less than m, then for those particular rows, and we'll use our logical indexing like we've done so many times. For those particular rows of the crisp array, all columns, just delete those. And for that particular row of the firms matrix, the firms array, set it equal to nan, and then we'll delete the nans in the if statement in the for loop. So that'll automatically, oh, I didn't run the m. That'll automatically get rid of all the data in here that relate to firms that don't have at least 100 months of observations. And it will put a nan value in each row in our firms array for those firms that don't have 100 observations. Then we're going to delete the NaN values from our firms array, which will the leftover portion of the array then will just be the perm nodes that relate to those firms that do have at least 100 observations. So this takes just a little bit because our crisp matrix is pretty big, almost 1 million rows. Again, this part of the code is a logical. For each I, this will tell us for that particular I, which means that particular perm node in our firms array. This logical will have as many rows as crisp does. And there will be a 1 in the logical if that particular perm node can be found on that particular row of the crisp column 1, and a 0 otherwise. Like for example, let's let I equal 1, so that firms 1, 1 is that perm number, well now it's NaN, but it was 1, 0, 0, 0, 0. And well, since I've already run this code, then this right here is going to give a logical which has a 0 in every, because that perm number is not there anymore because we deleted it with this code. But before that, it would have put a 1 on every row in the logical, where on the corresponding row in the crisp first column, it found that particular perm node, and a 0 otherwise. And you just take the sum of that logical, and if that sum is less than m, then that means that that perm node was found on less than 100 rows, which means it has less than 100 monthly observations. So we've deleted all the information from crisp we needed to. You see now it went from about 1 million rows down to 667,000 rows. And then in our firms array, we've put NaN for all those perm nodes. So a lot of these perm nodes don't even have 100 observations. So now we're going to write a line that gets rid of all the NaNs. Our normal way to do that, and I've done this many times before. I'm not going to explain the code. Done it in previous videos. Many times. So any row in the firms array which has a NaN value in it that row will be deleted. And I've already deleted the observations in the crisp array that correspond to those particular perm nodes that did not have at least 100 monthly returns. So what's left are 3,821 perm nodes that do have at least 100 months of observations, and a corresponding monthly observations that correspond to those perm nodes are right here now. All right. Now what I want to do is create a cell array for each perm node. So let I go start at 1, increment by 1, all the way up to the size of how many firms we have, which is in the rows dimension. The size of our firms double array in the rows dimension is 3821. Columns dimension is 1. We're using our size function. And again, like I've done in many videos, you put the array, and then the second argument of the size function tells it which dimension you want to measure the size, rows or columns dimension. 1 means rows, 2 means columns. So I is going to go from 1 all the way up to 3,821, increment by 1 each time. And we're going to create a cell array called crisp cell for each of those rows that correspond to the firms matrix. So for each perm node, we're going to create a cell array. So For the first one, 10006, we're finding all rows of crisp where 10006 appears in the first column, and all those rows, all columns, will go into its own little matrix. So here's crisp cell. So the first matrix corresponds to that perm node 10006, and here are all its monthly return observations. They're worth 173 for that particular firm over the sample time period of 1970 through 1990. Notice all these firms have to have at least 100. Here's one that has exactly 100. None of these should be less than 100. Those would have already been deleted with this step and this step. All right, now we can compute the unexpected return. I'm going to do it all in one fell swoop. Because for each firm, we have its own little matrix now. We can compute the unexpected return for each firm month. But we have to have at least 100 months. So for this particular firm, the first firm month we could compute the unexpected return is, we got to go down to row 101. So using the prior 100 monthly returns for this particular firm, we regress these 100 prior monthly returns for this firm on the corresponding prior contemporaneous market monthly rates of return for the whole market. So we regress rows 1 through 100 of column 4 on rows 1 through 100 of column 5, and that is doing exactly equation 3 in the paper. And we get an estimate of B1 hat and B2 hat. And once we have those two parameters from that regression, then we'll do our estimate for the unexpected return for this particular perm node. The earliest we can do it is for 1978 in the month of May. And we're going to put the unexpected return in column 6. So this cell right here, we want it to be equal to B1 hat plus B2 hat multiplied by this number, the actual market return in that month. And that will be our unexpected return. Oh, I'm sorry, that will be our expected return, right? That'll be our expected return, B1 hat plus B2 hat times the actual market return in this month. That's our expected rate of return. And we subtract that from the actual rate of return for this particular firm in that month. And that will be our unexpected rate of return for that firm in that month. For these other months for this firm before this, the unexpected return we can't compute. We just have to put NA in. Only can compute it starting in month 101. Now, but wait a second. That's the more complicated way of doing this. But if we do it that way, then like I just said, we won't be able to have the unexpected rate of return for this firm in any of these other months. And I don't think that's what they did in the paper. I don't think they did it that way. This is why replications can be hard, because unless the author is very clear, you don't know. It's kind of ambiguous what they did. All it said here, inclusion criteria, is that price data available on the CRISP tapes for at least 100 months. So I think what that means is instead of doing it that way, all they're going to do is they're just going to take all of column 4, regress it on all of column 5, get one estimate of B1 hat and B2 hat. Get one estimate of B1 hat and B2 hat, and then just use each of these actual market rates of return multiplied by B1 hat plus B2 hat times this is the expected rate of return for this month for this firm, and then take that and subtract it from the actual rate of return for this month for this firm. And so we can compute the unexpected rate of return for this firm for all these months, doing it that way. When you do it that way, though, it's not really fair because you're using, in other words, to compute the unexpected rate of return for this firm in 1970 January, you're using data that happened after that, which doesn't seem right. It seems like you can only do it using previous data, right? You can only form your expectation based on what's happened already, not looking forward into the future. But the way that they've stated their inclusion criteria is they just have to have at least 100 returns, and then you can compute. I think the first way I said it is the way that technically it should be done, but in this replication, we're going to do it the easier way. You shouldn't be able to compute the unexpected rate of return for this firm until at least row 101, because you have to use the prior returns to do that. But in this replication, I'm just going to do it the easier way. In fact, I have a video up where I show you how to compute abnormal rates of return. And in that video, I do it the first way I described, where you don't get the benefit of looking ahead. You always have to use data previously. And it's harder to code, and that also means that you're re-estimating B1 hat and B2 hat every time. Whereas in the way they did it, they just get one estimate of B1 hat and B2 hat for each firm, just using all the data. But my way, you use the first 100 rows and get an estimate B1 hat, B2 hat, and use that estimate to get the unexpected rate of return in month 101. And then in month 102, you use the first 101 rows and rerun the regression, get a different estimate of B1 hat, B2 hat, which will be basically very similar to what the first estimates were, but it will be slightly different and so forth and so on. But we're going to do it the easier way. And top of page 163 is what we were looking at, our equation there. So now I'm going to insert a LaTeX equation like I did in the previous video. And I'm just going to copy and paste what I have in my answer key rather than type it all for you. Copy and paste it there. And then for you following along in the video, if you're wanting to make yours look exactly like mine, I'll open Word and I will copy and paste it right here, make it bigger for you. That way you can pause the video and have that on your screen to type if you want to actually type out the LaTeX code. There it is. That produces this. So this is the equation we're using. We're estimating B1 hat and B2 hat. And I already said that I'm just repeating what's in the paper and what I've already said down here in the bottom little sentence. All right, so let's compute the unexpected rate of return. So let I go from 1, increment by 1, up to how many ever firms we have. Each firm has its own cell array, its own matrix. When I equals 1, crisp cell 1, 1 is the first firm's data right here. When I equals 2, crisp cell row 1, column 2 is itself a matrix, and it's the data for firm 2 and then firm 3. And then the perm nodes for those firms are these particular numbers, so forth. And then once we get inside a given firm's matrix, for J equals 1 to 1, the size of however big that particular firm's matrix is in the row's direction. So for the first firm, its matrix has 173 rows. Second firm has 252 rows, and so forth, or observations. So crisp cell, that particular matrix, row J, column 6, we're going to put the unexpected return. And the unexpected return is going to be the actual return for that particular firm in that particular month, which is in column 4, minus, so the unexpected rate of return for this firm, 1970 January, is going to be this number here, the actual rate of return, minus the expected rate of return. And the expected rate of return comes from regressing this column on this column, getting the estimates of B1 hat and B2 hat, and then taking B1 hat times the number 1, which is just B1 hat, plus B2 hat times this number. That's the expected rate of return. And so we're going to be subtracting that expected rate of return. So to get the coefficients, you have to do a regression, so we have to use the regstats function. Regstats has multiple arguments. The first argument is the dependent variable, which is going to be crisp cell 1i, all rows, column 4. That's the dependent variable. Second argument is the independent variable or variables. So if there's multiple variables, then variable 1 would be the first column of x, variable 2 would be the second column of x, variable 3 would be the third column of x, and so forth. And by default, regstats adds a column of 1s to x to estimate the intercept. You don't have to do that. You don't have to put the 1s in there. It automatically does it. If you want to estimate a regression not including an intercept, then you can't use the regstats function. You have to use the regress function. But regstats is more all-inclusive of a function for estimating regressions. And it gives more statistics. It spits out more statistics. It doesn't just spit out the beta coefficients and things like that. It also gives the t-stats and the coefficients, the p-values, the r-squared of the regression, the adjusted r-squared, things like that, and the f statistic, and basically any other statistic you'd want. I realize we don't need any of that stuff. All we need are the beta coefficients. But regstats is what I usually use for regression because of its all-inclusiveness. So the independent variable would be the market rates of return, which are in column 5, all rows. And then what model do we want to use? We want to use a linear model. We're using linear regression. And then what coefficients do we want? We just want beta. We don't want those other things. And like I've shown in a previous video, the output of this is a source array. So for example, let me show you. It's a source array, or a structure array, sorry, a struct array. And inside that array are two things. A character field called a source, which tells us that we use the regstats function, and then double arrays for each of the outputs, for each of the statistics that we wanted. We only wanted one statistic, which was beta, so here's the double array, and it's in a column vector. So that's the intercept, and that's the beta coefficient. And so, since this is a struct array, we want to say dot beta. We just want the beta part of the struct array. Let's just show you what that would look like. That's just the column vector of beta coefficients. First one being the intercept, the second one being the beta coefficient. And we actually want to make that a row vector. So we're going to take the transpose of that, which will just make one row, two columns instead of one column, two rows. And then we want to multiply this by the number 1. So basically we want to take what I'm trying to set up here. I'll show it to you in Excel. I'm putting the beta coefficients. I'm just going to pick random numbers. The intercept is 2 and the beta coefficient is 3. I'm putting that in a row vector. And I want to multiply that by the column vector of 1 and the actual market rate of return for that month, which let's say that's, I don't know, 0.02. And so a 1 by 2 vector multiplied by a 2 by 1 vector, you can't do matrix multiplication, right? What do I want? I want the intercept plus the beta coefficient times the market return. That's what I want, right? For the expected return. But how do I get that? Just multiply this vector by this vector, right? This gets multiplied by this. So the intercept gets multiplied by the number 1. So that's just the intercept. Plus this gets multiplied by this. But you can only do matrix multiplication if the number of columns of the first matrix is equal to the number of rows of the second matrix. In this case, 2. We have a 1 by 2 multiplied by a 2 by 1, and the output of that is always, the output of that would always be 1 by 1. You take the number of rows of the first matrix times the number of columns of the second matrix. That's the size of the output. But you can't do the matrix multiplication unless the number of columns of the first matrix, 2, equals the number of rows of the second matrix. You should know this for matrix algebra. So that's the reason why I had to set these beta coefficients up as a row vector and not as a column vector like this. That's why we took the transpose right here. So a 1 by 2, and this is going to be a 2 by 1. So we have in the first row 1, and then make a semicolon, not a comma. Comma means go to the next column. Semicolon means go down to the next row, and put the actual market rate of return for that particular security, which is in column 5 of crisp cell. And that should give the unexpected rates of return. We got the actual rate of return here. And we got the expected rate of return here. You can run this. And that should give us the unexpected rate of return for each firm for each month, for each firm month. And this may take a little bit to run, but it is what it is. There we go. So we have the unexpected rates of return for each firm month. So let's just check to make sure that we did this right. Let's take this number here. For this firm, 1971, August, its unexpected rate of return for the month of August was 13.33%, or 0.1333. And that should be equal to its actual rate of return, 16.41%, minus its expected rate of return. Its expected rate of return should be equal to its intercept plus its beta coefficient times the actual market return. So let's copy and paste some things into Excel and just verify. There's its beta coefficient from the regression from earlier. Here's its intercept. And you know, in Excel, I'm going to do it this way. put the number 1 there, put its actual market rate of return for that month right there. Whoops. Right there. And then just do this times this. This equal to this times this. Then add them together. And you have the expected rate of return, which is that. The actual rate of return for the particular firm in that month is, put that there. And then this is going to be the difference between the actual and the expected rate of return, which is the unexpected rate of return, 0.133312. So if we go and copy this number and paste it into Excel, it should be exactly that. And it is. So yeah, it's computing what we want. I always do that. I check a random cell. And sometimes it's helpful not just to check that first one, just come over here some random and just check like this number and make sure that, like, you can use Excel to run the regression of this column on this column to get the coefficients. And then with those coefficients, plug this actual market rate of return into those coefficients. Get the expected rate of return. Subtract that from the actual rate of return right here, and you should have that number. And if you don't have that number, that means our code is wrong. All right. Now let's go ahead and we let UE be equal to our unexpected earnings, with what we named that array. Our unexpected earnings reside in UE, and our unexpected returns are going to reside in UR. So we're going to vertically concatenate crisp cell using the vertcat function. And the vertcat function, like I've done in previous videos, all it does is take each of these individual matrices and it stacks them on top of each other. So it puts this one underneath this one underneath this one, this one underneath this one, back into a double array. So it's just one array. It's not a cell array. But this data goes underneath this data, and then this data goes underneath both of those, and so forth. And so we just have one overall big unexpected returns. Here they are. So we have the unexpected returns in column 6 for each firm for each month. Perm no, GV key, month, year. Actual rate of return for the firm in that month. The market rate of return overall in that month. And the unexpected rate of return for that firm in that month. We don't need these two columns anymore. We don't need column 4 and 5 anymore. We don't need the actual rate of return for that firm in that month. And we don't need the market rate of return for that month. We just need the abnormal rate of return for that firm in that month. So we can go ahead and delete columns 4 and 5 if we want to. So I'm going to do that just so we don't use the wrong column in our analysis. So UR equals UR all rows, columns 1 through 3, and then the last column, but not 4 and 5. There we go. And then we can seek to replicate. Now we can replicate figure 1. We have all the data we need now to replicate figure 1 from the paper. And for figure 1, see page 169 of the paper. Now, I'm debating, should I leave the rest of this to another video? I don't want to get these videos too long because they're hard to follow when they're really long. Maybe I can do it. Well, I guess I'll go ahead. Just continue. Maybe a long video, but so firm underscore month underscore ANN. Now I'm going to let that stand for firm month announcements. I want to get the unique firm month announcements. And that's in the UE matrix. In the UE matrix, this date here, this date is the fiscal year for the GV. There's the GV key. This is fiscal year. And this is the year month when for fiscal year 1982, they announced fourth quarter earnings. This is the year and month when they did that. So this particular firm in March, and we've gotten rid of the day because we don't care about the day, but in March of 1983, they announced their fourth quarter 1982 fiscal year earnings. And all these firms, like I said in the previous two videos, we were replicating their ball brown paper, and part of the requirements is that the firms all have 12/31 fiscal year ends. So all these firms have 12/31 fiscal year ends. We've already deleted all the firms that don't, to keep things simple. But in March of 83, this firm announces 1982 fiscal year fourth quarterly earnings. And we want all the unique firm month announcement date, firm months announcements. We want the unique firm month announcements because if you look at figure 1 here on page 169, it's all about the month relative to the earnings announcement. On the x-axis, we have the month relative to the annual report announcement date. 0 means that was the month where the earnings were announced. And there's no years here. It's just they're lumping their entire sample of unexpected earnings. This figure is made by summarizing their entire sample. They split their sample into two groups based on month 0. In month 0, when they announced earnings, that's when they announced earnings. If there was a positive earnings surprise, we're trying to plot the abnormal performance index for that particular subsample. And if it was a negative earnings surprise, we're trying to plot the particular performance of that subsample. From -12 all the way up to 0. And so we're going to lose a lot of firms by doing this, by having to go all the way back 12 months in the past. We're going to lose a lot of firms that don't have 12 months prior return data. We can't find it over here in our UR matrix. They've gotten deleted. Or they had enough information to get in the UR matrix, right? They had at least 100 monthly returns over the sample time period. So we have their unexpected return for lots of different months in lots of different years, but we don't have them for the right months and the right years to, like, for example, let me give you an example. So say this particular firm, there's this GV key. It announces on March 3rd, 1983, for fiscal year 1982, it announces its earnings. Its unexpected earnings are negative, and its unexpected earnings per share are negative. We don't care about the magnitude. We just care about the sign. So this firm, month 0 for this firm is 1983 March, and this firm would be in the negative surprise category. Now, for this particular firm, GV key 1045, we got to find that GV key 1045, which is in column 2 over here, and then make sure for that firm that we have the monthly rate of the unexpected rate of return in March of 83, in the 12 months prior to March of 83, and in the 6 months post March 83. So in the 18-month time period. And if for any one of those months we don't have the monthly rate, the unexpected monthly rate of return for that particular firm, if we're missing in any of those 18 months, then that whole firm gets thrown out in all of its monthly return time series. You see, and it gets thrown out of. It's not part of figure 1. You see the stringent criteria. You have to have data for 18 months. both in return. You had to have unexpected return data for each GV key monthly announcement date in the UE matrix. For each of those, you have to have the corresponding returns that correspond 12 months prior to this and 6 months post this in the unexpected returns matrix, and that's just very stringent. That's where we're going. So we get the unique UE, all rows, columns 1 and 3 in the rows direction. We're using the unique function, and we're getting the unique firm month announcements. I think I've messed up here. No, I haven't. This is right. The unique firm month announcements. So for each firm month, we want the unique combinations. That's a unique combination. That's not repeating. That's not repeating. You see, we don't just want the unique month, but we have the unique firm months. So we're not just taking the unique values in column 3. We're taking the unique values in columns, treating columns 1 and 3 as a double, as a pair, the unique pairs. So here are the unique pairs, unique firm month announcements. And then I'll explain this when I get through. We're going to go through this unique firm month announcement array, row by row, and we're going to ask the question if and let me see what I did here. If firm month announcement row I, all columns equals UE, all rows, columns 1, 3, so anywhere where you find that particular firm month pair, firm month announcement pair in the UE matrix, this is a logical, right? There's a 1 on the row if it found that particular firm month announcement pair on that particular row of UE columns 1 and 3, and a 0 otherwise. So if we take the sum of that, so let's see what this logical looks like. Let's see what the logical looks like. Oops. I'm going to call it little a. Whoops. That way I have it saved just so we can see what it looks like. It's a logical. And row 1, all columns of this here is this. So it's a logical. Where do we find this in UE? Column 1. You see it's like this. So we found in row 1 of UE column 1, we found this, and column 3, we found this. And so in the logical, both of these are given a 1. Where in row 2 of UE, we found the 1045. But in row 2 of UE, on column 1, we found 1045. But in column 3, we didn't find 1984-02. And so that particular, we only want to look and see trying to explain this. So now if we take the sum of A transpose, and we'll call that B. So A is on the screen. We take the sum of A transpose. We take the transpose of A. So the rows become the columns. We take this, so 1, 1 becomes 1, 1. Then 1, 0 is a column beside that 1, 0. And then 1, 0 is a column beside that 1, 0. We take the sum of that. That'll give the sum of each column, right? So B will be the sum of each column. And columns whose sum is 2, we want to find. So C will equal find, B equal 2. Columns whose sum is 2, we want to find those columns and locate them. And that'll tell us on which row it happened. That'll tell us which particular row of UE we were able to find that in column 1 and that in column 3. So C is 1 on row 1 of UE, because that's where in B the sum was 2. You see, I've done these 3 steps here. And then it should be UE of that particular row, column 4. We're checking. We're checking to see if that's bigger than 0 or less than 0. So to put it all together, so sum of we want to take, so A equaled this, and then we did B was the sum of A transpose. So A is this. So we need to put parentheses around all of that. Take the transpose and compute the sum. That's B. And then C equals find where that equals 2. So where this equals 2, put the parentheses there. Find. So if this is greater than 0, then we're going to let firm month underscore announcement row I column 3 equal 1. Else we'll let firm underscore month underscore announcement I3 equal -1. End. And so that will give us, for each of these unique firm month announcement dates. What did I do wrong? Firm month announcement. Oh, I should have done right here, columns 1 through 2, not all. Because after you get to the second row of this, now it's fine on the first row, but then I've assigned to column 3 either a 1 or a -1. So now there's 3 columns. And if I do all columns here, it's going to pick up all 3 and it's going to be wrong. Okay, I need to do it like that. Right. And so now for each unique firm month announcement of earnings, we know if it was a negative surprise or a positive surprise. You know, a faster way to do this that I'm just realizing is just come back to here. There's a simpler way to do this that I'm just thinking of off the cuff. In column 6 here, just put a -1 if this is negative and a +1 otherwise. In column 7, put a -1 if this is negative and a +1 otherwise. And then once I have those things in columns 6 and 7, then I can just get the unique firm month announcement dates from this with their corresponding values in column 6 and 7. That's so much faster. I mean, this works as well, but and then here I could just so I could let me think. So a faster way of doing, or easier way of doing this is first up here. So yeah, that accomplishes what I want, but maybe a better way of doing it is for I equals 1, increment by 1, going all the way through size of UE in the row's direction. So if UE I column 4 is negative, then let UE I column 6 be equal to 1, else let UE I column 6 equal to -1. And that if then, and then start a new if then. Let me put that down there. If UE I column 5 is less than 0. So this is the EPS column. Then let UE I column 7. Oh, whoops, sorry, I did this wrong. This should be a -1. This should be a +1. Equal -1. I should have semicolons here. Else let UE I column 7 equal +1 in that if did, and then in the for. So if I do it this way, then UE has corresponding I'm trying to think now, firm month announcement. Then I could do firm month announce equal unique. So I'll go ahead and delete firm month announce because it won't have been the code that I did to make that was before this, but I already deleted that code because I'm going to do, I think this is an easier way to do it. Equal unique. Unique UE all rows, columns 1, 3, and the rows. Oh, what happened? Oh, I forgot to put a like this. All right, this is what I had before, and then I want to put in column 3 a whatever's over here. Whoops, where's the UE? Whatever's over here in column 6, corresponding to that particular firm month announcement. Now I can do something like for I. Or should I just keep it the way I had it? For I equals 1, 1. This is probably more intuitive to follow, though, what I'm doing here versus what I typed earlier. I think what I typed earlier is faster and easier. Like, it's less code, but it's harder to follow. Maybe I should just keep what I had. I'm just going to keep what I had earlier. So I'm just going to get rid of all of this. And here's what I had earlier. Oh, I had this down here. Sorry. And here's what I had, what I had come up with. I'd done this first. What I didn't do is this. I did not do that. Kept that like that. And then I had run this code and I'd gone through that. So that had put the corresponding, in the column 3, it had put a corresponding -1 and a +1 where we needed it. And then what we need to do then is just copy and paste this code and change this to column 5, change this to column 4, and run this, and then that should put in column 4 of the firm month announcement, it'll put for this particular year month was the EPS negative or positive. -1 means negative, +1 was positive, right? Because in column 4 here we have earnings, regular net income. And this column here tells whether that's negative or positive. And then our second variable, variable 2, is EPS, and this column here tells whether that's negative or positive. Right? Variable 1 is net income and variable 2 is EPS. And we're trying to replicate this figure for variable 1 and variable 2. We didn't do variable 3 in our replication. We're just replicating variable 1 and variable 2 portions of the figure. We just have the signs now. And most of the time, if net income was negative, then earnings per share were negative. But not always. Sometimes the signs weren't in alignment with each other. And I'm trying to... And the reason that is because the numerator in computing earnings per share, because I'm using the EPS variable from CompuStat, and their numerator for computing earnings per share is different than just net income. So net income could be negative, and earnings, and their earnings in their numerator of computing earnings per share positive, and therefore the EPS positive, or vice versa. Because their earnings they use in the numerator of computing earnings per share is not net income. It's net income minus some things. Minus some things and plus some things. So it's income excluding extraordinary items and things like that. So I think, or no, the EPS variable I originally used, let's see, it was EPS PI, which is earnings per share. You can go in and look at the variable definition of this variable. NI is net income, but EPS PI if you go through here, they don't always agree in sign, although most of the time they do. Like right here. EPS PI, you can go in there and into CompuStat and figure out what is that variable. We could go on CompuStat now. But anyway, doesn't matter. You can do that on your own. So did I run this already? Yes, we have the signs. Now the next of this, I'm looking at my answer key here and I'm just trying to remember what I did. What do I do next? Okay, now what we're gonna do next is in column 5, we're gonna put, so this is month 0 for this particular firm, for this particular year. This is right according to the figure. Month relative to annual report announcement date, 0 is the month that they announced. And so what I want to do is find 12 months prior to this. I'll put that in column 5, and 6 months post this and put this in column 6. I want the month 12 months prior to this. And 6 months post this in column 6. So how do I do that? This right here is not a date, it's just a number. Right? It's a double array. So the data types of these variables are double. So how do we get the month 12 months prior to this? Right? There's 12 months in a year and then it starts over, right? Goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and starts over 1, 2 for the next year. So, but we can do something tricky here. We can do something clever without having to convert this to a date. If we convert this to a date, we can use some date functions to get 12. We can just subtract 12 months and get the month 12 months in the past, in the year. But then we can't use a double array anymore. We got to use a table array, and then it just becomes more complicated in terms of using different data types. And I don't want to do that. I just want to think of a clever way of just taking a number, and you can't just subtract 12, right? You can, depending on what the number is, and you'll get 12 months prior. But what you do is, if we divide this number, you'll see what we're going to do here. So for I equals 1, increment by 1, all the way up to the size of firm underscore month underscore announcement. Our unique firm month announcement dates. And I'm going to let J go from 6 no. Now I'm just going to say if the modulus, so the mod function, the modulus of, now the mod function has two arguments, a comma m, and it takes the, it finds the remainder of the result of dividing a by m. It gives the remainder. So 12 divided by, if a is 12 and m is 5, 12 divided by 5, the remainder is 2, right? Because 5 goes into 12 2 times. 5 times 2 is 10, and then there's a remainder of 2 left over. So the result mod 12 comma 5 would equal 2. So that we need this remainder. Firm month and row I column 2, that's the date. That's the date column. And we're dividing that number, dividing this number here by 100 and finding the remainder. And if that remainder is not equal to 12, then, like, let's just go for an example. Like if we do mod 1983 03 100. The remainder is 3. If the remainder is not 12, then we're going to let firm month underscore and I column 5 equal firm underscore month underscore and I column 2 minus 99. You'll see this works. So 1983-03 minus 99 is the number 1982-04, which, so we go 11 months back in the past. April of 82. So for a firm who announces earnings in March of 83, and that's month 0, April of 82 is 12 months in the past, right? May of 82 is 11 months in the past. June of 82 is minus 10, and so forth. Does that make sense? In other words, from April of 82 through March of 83, that's these 12 months. But if the remainder of taking that number, dividing it by 100 is 12, then so else, we're in the else condition, then just subtract 11 from it. That way, like, if we have a date that's 1983-12, and if we take the mod of that 100, what is that? The mod of that 100 is 12. Then if we subtract 1983-12 minus 99, that's not going to work. That'll give us 1982-13. But we don't want, we want to just subtract 11. And that'll give us 1983.01. You see? So we run that, and that gives us the month that is. So from this month through this month, that takes us from here through here. And then in the column 6, we want the month that's 6 months in the future, or to take us from here through here, I guess 5 months in the future. 0, 1, 2, 3, 4, 5 is 6 months. So, and you can make sure that this is right. This lines up, right? 83, March of 83 through February of 84 is 12 months. That's 12 months, right? That takes us from -12 all the way to 0. And you can make sure everything works. February of 87 through January of 88. Through January of 88. February of 87 through, all the way through, not to January 1st of 88, but through to January 31st of 88 is 12 months. And so forth and so on. And if any of these ended in 12, which they shouldn't, I mean, there are some though that do end in 12. So it took all the way until the end of the next year for the company to announce their fiscal year of the previous years. Like their fiscal year ended the previous year for all of these companies. Like this company is announcing fiscal year 1982 fourth quarter earnings in March of 83. And so most of these companies announce by no later than April. But there are some that announce way in August of the next year, and even some that announce in December. If they announced in December, then we would fall into this particular category, and we would just have to subtract 11. You can look and make sure that it's correct. You can look through here, and we could write some code down here and find any rows of column 2 where the month is 12, and see did it do the right thing over here in column 5? Did it go 12 months in the past? Most of these, though, are February, January of the next year, or March. So. So that gets us, all right, so I think I said something wrong earlier. So this will get us the month 12 months in the past. Then we want the month 11 months in the past, then 10 months in the past, then 9 months in the past. We want them all. We want all 18 months that surround this time period laid out. So what we're going to do next then is for I equals 1, increment by 1 all the way through size of the unique firm month announcements, dates. And then for J equals, we're going to start J at 6, increment by 1, and go all the way through 22. And that'll bring us, that'll enable us to fill in column 6 through 22 with the 18, well, I guess 17, because this one's already there. So 22 minus 5 should be, or 5 through 22 is 18, right? 22 minus 5 plus 1 is 18, yeah. We're going 6 through 22. So we're going to say if mod affirm underscore month underscore an of row I, column J minus 1, the previous column, 100 is not equal to 12. Then firm underscore month underscore and row IJ equals firm underscore month underscore and row I J minus 1 plus 1. Else firm underscore month underscore and IJ equals firm underscore month underscore and row I J minus 1 plus, and I'm going to write it like this, 100 minus 11. I mean, I could just put 89 there. But I'll write it that way. In other words, and you'll see that this way makes everything work out. So you just have to add 1 here. If the previous, you just add 1. You can't just keep adding 1 though to from the previous one. Because once you get to 12 right here, if I add 1 to that, you get 1982.13. But I got to go 1983.01, and that's why we're in this else condition. Once you get over here to where we have 12 as the month, then so we've gotten yeah. Once you get over here, we have 12 as the month. Then you have to then we're in this condition. When we get to this column right here, row 1, column 14, row 1. So I equals 1 and J equals 14. Then mod firm month and I J minus 1 100 is equal to 12. Therefore, firm month and 114 has to equal firm month and 113. Not plus 1, but plus 89. And it actually works. Plus 100 minus 11. And you'll get the right number. Taking advantage of, we have a base 10 number system, and with months, it's kind of like a base 12, right? The way months work. And then you go, so this is the month 0. So here are the 12 months leading up to the earnings announcement, including the earnings announcement month. And then here are the 5 months. I'm sorry, here are the 6 months after the earnings announcement. 1, 2, 3, 4, 5, 6. So there's actually 5 through 22 is 18, right? Yeah, that's 18 months of data. Right. And then now all we need to do, we only need to keep certain columns of firm month and now. Or no, now what I want to do is create a cell array for each row. For each row of firm month and, I'm going to create a cell array. And I just need column 1 and then 3 through end. I don't need column 2 anymore. I mean, you can keep column 2, but I did it this way in my answer key. And you'll see why this becomes important. We got the perm no. We got the sign of the net income. We got the sign of the EPS. And we have the particular months that correspond to this. And we know in column 15, that's the month, that's the announcement. That's the 0. That's the 0. right? Because that's 12 numbers right there. Minus 12, minus 11, minus 10, minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2. Should be minus 1. This should be 0. Oh, this is minus 11. Right, so this is the... Anyway. This is the right way to do it. It's hard to explain exactly how it lines up, but this is the right way to do it. Actually, I may have not done it exactly right. Maybe because the sum of minus 12 through 6 is 19, not 18, right? Because you're including 0, I think. So maybe I don't quite have enough dates, but I'm going to do it this way. If you add more, then it makes it even more unlikely. You're going to lose more and more firms. You're going to see we're going to not have very many firms in our final sample. And that's why in their paper, if you look at their paper, I think, where do they talk about it? The actual number of firms that end up in their final sample that this figure is based on is only like 269 firms, I believe. 261 remaining firms right here. They do not have a lot of firms in their sample. You start out with lots of firms, but then after all these requirements, you lose a lot of firms. See, they even say our selection criteria may reduce the generality of the results. The subpopulation, in other words, the number of the firms that are left in their sample do not include young firms, those which have failed, those which do not report on December 31st, and those which are not represented on CompuStat, the CRISP tapes, and the Wall Street Journal. They got the earnings announcement dates from the Wall Street Journal. They did do a replication of their study on a different sample, produced results which conform closely to those reported below. But anyway, and in our particular sample time period that we chose, 1970 through 1990, we actually have less firms than they did in their sample. We have like 209 or something like that, you're going to see. I can't remember the exact number, but... All right. Now what I want to do is first set row 2, columns 1 through 3 equal to nan. 1 row, 3 columns. So these will be nan. And then starting in column 4, so for j equals 4 through 1, all the way through the size of firm underscore month underscore and cell 1i in the column's direction, which be column 4 through column 21. So if, all right, how to say this? So if you can, so wherever we find, if we can find this particular firm in the unexpected returns matrix, column 2, that's where the GV key is. And if we can find this particular date in column 3 of the unexpected returns matrix, then we can then what I'm going to do is put right here the actual unexpected return. So that's what we're going to do. So if firm month and cell 1i row 1 column 1, that's where the GV key is, equals UR all rows column 2, that's a GV column, and firm underscore month underscore and cell row 1i row 1 column J, and J is starting on 4 now, right? J starts at 4, which means we're right here. If this date can be found in column 3 of the UR matrix, which is the date column of the UR matrix, so that's a logical right there. This will just be a big logical. So if we take the sum of this logical and we don't get 0, then firm underscore month underscore and cell row 1i, I'm sorry, firm month and cell 1i row 2 column J will equal UR, and the place where this occurs, the last place where this occurs, so find where this last occurs, that particular row of UR column 4. And we say last because, or else, sorry, else if this condition doesn't hold, if it can't find, which is highly likely, then firm underscore month underscore and cell 1i row 2 column J equal nan. And so if we can find this firm in the unexpected returns array, we can find this date in the unexpected returns array, then the last place where we find the last row in the unexpected returns array where we find this as the GV key and this as the date, we put the unexpected return right there. And that unexpected return is in column 4. And why do we say last? Because there may be more than one time where in the unexpected returns matrix where we can find this particular GV key and this date. And the reason is because remember, the GV key is the firm and the permno is the security. So a given firm can have multiple permnos, right? A given firm can have common stock class A and common stock class B, for example, 2 different permnos, same firm, same GV key. So the same date would be there where you would find that same firm and the same date, just different permnos, different unexpected return numbers as well, because there's 2 different classes of stock. But that's why we say the last time you find it. Just pick the last one. Or I could say the first time. In other words, for that particular firm, we're using one of its unexpected return numbers. for one of its classes of stock, but not for both classes of stock. I guess we could take the mean of I guess I could do the find. I could just do mean here, and then you don't have to put last. Then if it finds multiple instances, multiple securities for that particular firm and date, then it would just take the mean of all those unexpected returns. I guess you could do that. So let's remove the last here. And we don't even need the one here. One just, it grabs one observation of all the ones that it found. Now, usually it's only going to find one. But if it finds more than one, it grabs one of them. And which one does it grab? It grabs the last. But we could just take the mean. You know, we can just do the mean here if it grabs more than one. Change our code to that. Let's run this. Now this is going to take a little while, I think. But we'll see. You can see this figure 1 is actually somewhat tricky to replicate. There we go, we're done. So if we go here. So we were able to find for this particular firm, this particular date, we found at least one instance. We must have found at least one instance, otherwise this would be assigned a value of nan here. We found that firm in the unexpected returns. So we had unexpected returns for that GV key on that for that month, and there that was the number, and so forth. Now what we want to do is delete all firm years if we want to delete the whole I don't know how to say it, but if a given firm 1045 for example doesn't, and it announced earnings on, if we recall, March of 1983 for fiscal year 1982, that's when it announced its earnings. You could see the unexpected return was high the day that it announced. But if there's a nan value in any one of these cells here, that means we don't have the unexpected return for that particular firm surrounding all 18 months of its earnings announcement date. Therefore, we delete that particular firm. So that's what we want to do next. So if the sum of isnan firm month underscore and cell 1i row 2 columns 4 to the end, if that sum is greater than 0. So if we do isnan of these numbers, it's going to be a logical row vector that has a 1 if there's a nan anywhere in there and a 0 otherwise. So if the sum of that logical is greater than 0, then that means there's at least one nan value there. Then we're going to let firm underscore month underscore and cell 1i just equal, just delete it. Delete all firm month announcements which don't have 18 months of unexpected returns surrounding the earnings announcement month. And then we'll set firm month and row I, all columns, equal to nan as well. Because remember, for each one of these rows, we have a corresponding cell array over here, and we'll just set that row all nan. So when we run this, you can see lots of rows get assigned to nan. We're only left with certain firm month announcement dates, and that's because lots of these cells are set equal to are deleted. Right now, firm underscore month underscore and cell or and all is nan, or we could do any. If you find, for here, I want to delete all the rows where you find a nan value in all of the columns or in any of the columns, because you find it in all, you're going to find it in any, the way we did it. So I'll be specific, because I did put a nan value in all columns there, so I'll do all. Either way you're going to do it, you're going to get the same thing though. So we're deleting those rows of firm month and. And then for the firm underscore month underscore and cell, we want that just to equal firm underscore month underscore and cell. And then I'm going to do something here that you just have to just memorize, or you can copy and paste. I forget this code every time. How to delete permanently empty cell arrays from a cell array, or empty double arrays from a cell array. And then this is how you do it. So firm month and cell. I want to get rid of all these empty ones. Just remove all those. And just leave the ones that aren't empty, but remove all the ones that are empty. So let's run both of these lines. And you can see it removed all the ones that were empty. And then for the firm month and, we're left with the corresponding 1,703 unique firm month announcements that had the appropriate data to replicate figure 1. Had the 18 months surrounding them. All right, now we're really close. Now what we can do is we can compute the API value, the abnormal performance index, for each month surrounding, for each of these months surrounding each of these firm month earnings announcements. For each of these months, we can compute the API, the abnormal performance index. And the abnormal performance index, they define that up here, right here, as this. And I should put that in my code in terms of a LaTeX. But it says this traces out the value of $1 invested in equal amounts in all securities at the end of month -12. That is 12 months prior to the month of the annual report, at the end of month -12. So you hold it for all of month -11 through month M, as you can see here. So if M equals -11, then you're just, what that corresponds to is just the abnormal performance index for this first month. If M equals -10, then you're computing the abnormal performance index as of the end of month -10. So from -11 through month -10. From -11 through month -10. And all the abnormal performance index is it's just 1 plus, it's the product of 1 plus the individual month's abnormal return. The average of 1 plus the product of the individual month's returns. So that's all it is. It's like you invested $1 in the in all the securities, an equal amount, 1/n. You know, if you have $1 to invest, and there's N securities, you put 1/n of $1 into each of the N securities, right? At the end of month, you do exactly what this says here. So it's not the abnormal return on the portfolio, but it's 1 plus the abnormal return on the portfolio that you're plotting, basically. It's like how your dollar is moving, how the value of your portfolio, you have your $1 at the beginning right here, and you invest it in stocks. And you plot how that dollar is performing as we get up towards, as we move from -12 all the way up to the day that the month that they're going to announce earnings. And all the stocks you're investing in are the stocks that have the same sign on their unexpected earnings. The positive surprise stocks is one portfolio, and the negative surprise stocks is another portfolio. And that's the whole point of their paper, to compare the performance of the two. So all we have to do then is for I equals 1 to 1, increment by 1 all the way up to the size of firm underscore month underscore and 1. I want to call it firm underscore API overall. Now here, because in their paper, they have the total sample where you invest $1 in all the companies, regardless of the sign of their unexpected earnings. And this is what the API should look like over time. It should go down. But once it gets to month 0, it shouldn't really go down. Well, it does still go down some. Not much. But overall, your $1 invested, regardless of the sign, take all the companies, and at the end, 18 months later, it should be worth about, what is this? 98.5 cents. So a 1.5% loss. So we'll do the API overall first. Row I, columns 1 through 3. Will equal the firm underscore month underscore and cell 1I, row 1, columns 1 through 3. And then for J equals 4, increment by 1 all the way to the size of firm underscore month underscore and cell 1I in the columns direction. Let firm underscore API overall, row I, column J, equal the product of firm underscore month underscore and cell 1I, row 2, columns 4 through J, plus 1. And so we get in here. Regardless of the sign of the unexpected earnings or the sign of our variable 2, which is EPS, if we don't look at the signs of the unexpected earnings or the unexpected EPS, and we just, the API for this particular company here just traced out -12. So we start with $1, and then in the first month we have a negative 0.0126 unexpected rate of return. So we add 1 to that number. In month 2, we have a positive 0.1326. We add 1 to that number. So this is month -12 or month -11. This is month -10. And so if we were just, what would the value of our portfolio be at the end of month -10? Well, we would take the number 1 plus this number multiplied by the number 1 plus this number. And that would be the value of our portfolio. It's this formula right here. Just this part. The V_NM are these numbers. Are these individual numbers. So this should do it. So firm API overall. We just, for each stock, we find its API plotted out over the 18 months. We have each stock in here. Each stock, each announcement date, right? This row right here corresponds to this particular stock in, and we know that in column 15 it announced earnings on this in this month. So for fiscal year 82, and here's its API plotted over the 18 months. And the same thing for each of the firm month announcement dates that have the 18 months of data, we plot out the API. And then all we have to do for the overall is just take the mean of each of these columns. And that mean will be this. And then for the positive earnings surprises, variable 1, then we look in column 2 here because that corresponds to the net income variable. Just the positive, the ones where there's a 1, find a mean. And that'll correspond to the variable 1 here. For variable 2, column 3, we look for the positives that were the 1 and find the mean. And then for down here, we find the, for variable 1, which is in column 2, we find the negatives and find the mean and so forth. So all the information is right here. It can be computed from this. So API overall equals 1, the mean of firm API overall, all rows, columns 4 through end, this is the API for the whole sample. For the 18 months. In other words, our dollar starts at -12 at $1. At the end of -11, our dollar is worth that much, the overall sample, and so forth. So overall, our API for our 20-year sample time period ends up slightly positive. It's going to be up here at 0.03. It's actually up here overall. Our total sample So we're not able to replicate this line. It's not overall negative. It's up here positive, it looks like. Then, of course, it's a different sample time period. But it just shows how sensitive their results are to the change in the sample time period. They are sensitive to it. You can't always find their exact result if you change the time period. All right, for positive variable 1, net income, we find the mean of firm API overall, where 1 equals firm API overall, all rows column 2, because that's where variable net income was. It's in, if this is a -1 in column 2, then net income was negative, which means negative earnings surprise. If it's a +1 in column 2, that means net income, the unexpected net income was positive earnings surprise, so forth. Firm API overall. So those rows where 1 equals columns 4 through end. So, I mean, it just picks out those rows here where in column 2 there's a 1. So it just picks out columns 4 through 21, just those particular rows where in column 2 there was a 1. And it stacks all those on top of each other and finds the mean of each column. And you do the mean like that. So we could we can run this and just verify that everything is, check it in Excel to make sure we're doing it right. This is API for the positive net income subsample. Let's just verify that in Excel. Let's run this, get some numbers. Of course, we put a 1 at the beginning as well so that we could replicate the figure. The figure has a 1 starting at -12. Right, our dollar starts off at $1. And yeah. And you see we end up way above, way down here at 9.88%, 1.0988. So we end up here actually for our variable 1. Total sample ends up like right here. And we're going to plot it actually so we can just compare the plots. Picture's worth 1,000 words. But let's make sure that these numbers are right. So if we take our, where is it? We take our overall sample here. Let's put it in Excel. We can filter on column 2. This is variable 1 or net income. And this is variable 2 or EPS. Filtering on column 2, just finding the positive where it's +1. And then finding the mean of, let's say, column 1 here. We get 1.005684751. And this is 1.0057. But that's rounded, so we got 1.00568471. Now if we put this here, 1.00568475. I don't know why this mean should be, but I mean it's basically the same thing, right? $1.00568471, which is exactly what we have, 1.00568475, and then that digit would be a 1 because a digit next is a 9. So yeah, this is right. We're doing things correctly. And then you just basically just copy and paste this and just finish it. So negative ni would be where -1 equals and change this to negative. And then positive EPS. So we have variable 1 and variable 2. Change this to EPS. And then finally negative EPS. Then change this to -1. And yeah, so let's run that. And then finally, we can actually plot the figure. So we'll do figure, plot. On the x-axis, we're going to plot -12 through 6. And then we're going to plot API overall. And we're going to make the color of that line going to be solid black. And then we'll plot also on the x-axis -12, 6. And on the y-axis, we'll plot API pos ni, positive variable 1. And we'll make the color of that black, but we're going to be dashed line. And then, you know, I'll just copy and paste this. And then we're going to also plot -12, 6, positive EPS. And we'll make the color black. The K represents black, and then 2 dashes. And, oh, not positive 12, 6, -12, 6. And then we'll plot negative ni. And we're going to make that also dash line black. But it'll be down in the negative portion, so you'll be able to distinguish it from the one that's in the positive portion. And then finally, we will plot negative EPS. And we will make that black color too. Right. And then as far as, so we're going to plot a line at 0 on the x-axis. A vertical line. It's going to be black vertical line. Because they have a vertical line right here at 0. You see? So we use the x-line function. For our x label, we're going to label our x-axis month relative to annual report announcement date. We'll make our font size 14 for the x-axis. In other words, this here. And then for the y-axis, the abnormal performance index. It's been a while since I've done a graph in a video, but this is how you do it. You use the plot function. You use the plot function and you tell what you want on the x-axis and what you want on the y-axis, and then if you have, and then also what color you want the line to be, and what shape, dash, dot, things like that. So K means black. Colon means, I think a dotted line. Just a color here and no dot or dash or anything just means solid. It'll be solid. So this means a dash. This means 2 dashes. The line is like separated. You'll see what I mean. If you want to put like B, that means I think B stands for blue. BR is brown. R is red. Y is yellow. If you don't specify a color or a form for the line, then it just automatically chooses it for you. And if you got multiple things that you're plotting, then it'll pick rainbow colors. But it'll make them all solid lines, not any dashes or dots. But when publications, it's good to, because usually they can't print color. So you can make these different colors, but you won't be able to distinguish the one from the other because they print in black and white. So you have to make it dashed or dotted so that people can know what line is which, especially if they're almost overlapping each other. So that's what I'm doing here. Turn the grid on. Do they have the grid on? They don't have the grid on. I guess I don't have to have the grid on. They have the grid on the, I guess they got partial grid lines on, but maybe we don't. Maybe we won't turn the grid on and we'll just see how it looks. And then we're going to give it a title. Abnormal performance indexes for various portfolios that are based on the earnings surprise. And the legend is total sample. So the legend corresponds to what you have on the y-axis in order. So the first thing was API overall. We want that to be labeled total sample. Then API positive net income. We want that to be labeled positive net income. API positive EPS. We want that to be labeled positive EPS. The negative net income. The negative EPS. And then where do we want this legend? We want it in the, so we have to specify a location for the legend in this argument. We don't have to. If we don't specify it, it'll choose the best location that it thinks. But I don't always like the location where it puts it, so I'm going to put it in the northeast. Choose a font size, but then we can move it. You'll see what I mean. Font size for the legend, I'm going to make the font size 12. And there we go. Let's go ahead and plot the figure. And unrecognized function or variable API overall. Oh, I see. The API overall, I did not capitalize the O here, so didn't recognize it because I had it capitalized here. All right, so here we go. Let's go ahead and close. All right, let's go ahead and run. F9. Specify error using plot. Specify the coordinates as vectors or matrices of the same size. Oh, okay. So these things aren't the same size. They should be. They're all 1 by 19. And we're going from -12 through 6. That's also 19, right? Oh, let's see. Where is it messing up? So these are all 19. I am confused. Negative 12.6. Specify the coordinates as vectors or matrices of the same size. I mean, they obviously have to have the same size. I can't find where my error is in what I've typed, so what I'm going to do is just copy and paste from the answer key over what I've just typed, just to save time here. Which hopefully, the only thing that looked different is I had a grid in the answer key. What I didn't remember, we didn't put the grid. Let me turn that off, and then just run this. If this doesn't run, then that my answer key ran fine without an error. I don't know why this would run with an error. So there must have been something, I must have had a semicolon or something missing. But anyway, so there, right here, and then what we can do is we can move this down, even though we specified it to go in the northeast corner, we can move it down here. Then we can go ahead and save our figure. And we'll save it as a PNG file. And we'll save it as figure 1. I actually already have it saved as this, so we'll just keep it saved as that. And I actually did this. All right, we'll talk about that in a second, but we'll place it. So we have this figure saved. So here's what our figure looks like, and here's what their figure looked like. You can see our total sample. And I think it's helpful to have the grid on, actually. Because see, they do have a Y line, or at least I need to add a Y line. Let me add a Y line. They have a Y line. You don't have to have a grid everywhere, but at least to add a Y line. Let's run this. Somehow that messed up something when I added the Y line. Well, you know what? Let me just turn the grid on then. I don't want to spend the time in the video to figure out how to add just a one solid black Y line, but and then let me save this as figure. So you can see that we find similar results. We start at 1 for the positive net income, the positive earning surprises, returns. I mean, we find overall similar results. Returns for the positive earnings, returns for the firms that are going to announce positive earning surprises at month 0, their returns start to move up 12 months in advance. And then once they announce, we don't find that the returns continue to drift upward like they found and then settle back down. We find actually that the returns kind of settle off, but then they go up later. And then for the negative sample, and we end up at 1.0988, and they end up at 1.07 something in terms of the API. And then for the negative, so a 9.88% return overall from -12 to +6. Our overall, not considering the sign of the earnings surprise, overall, you can see we end up at over here, not down in the negative like they did. We don't have enough. Where's our EPS? That should be on here. I don't know where our EPS is. It should be on here. Oh, down back here, I need to change this. EPS is was in column 3, not column 2, right? I just recognized that. We take API overall, we're at firm API overall. Where is it? And column 3 is EPS. So yeah, I need to run this again. And then run this again. There we go. There we go. Now I'll save this. Yeah, because before this should be column 3 here. I just had it as column 2, so the positive EPS was superimposed on the positive net income. They were the same line because it was the same code. You see what I mean? So, but no, it's what it should be. So we do find for our variable 1, which is net income, that the positive is higher than the EPS variable 2. They found the opposite. Variable 2 is higher than variable 1. And down here, they found variable 2 went lower than variable 1. We find variable 1 goes lower than variable 2. But, I mean, the figure does look, in some sense, it's qualitatively similar. Of course, our sample time period in this figure is 1970 through 1990, not 1946 through 1966, which is their sample time period. But you can see our y-axis looks similar to theirs. Theirs ranges from 1.1 all the way to negative 0.88. Ours ranges from 1.1 to 0.94. Did I say negative 0.88? From 1.1 to positive 0.88. And ours ranges from 1.1 to 0.94. So qualitatively, we're similar, but some of the big differences are we don't see evidence after the earnings announcement if it's a positive surprise of the returns continuing to drift upward. And then for a negative earnings surprise, we don't see evidence of the returns continuing to drift downward like they do, at least for our sample. So that's a replication of figure 1. They do have some other things they do in the paper that I wanted to replicate, but I suppose I can save those for one last video in this series, and they won't take very long at all. So in the next video, I do want to replicate. Of course, we could replicate table 6. How many for variable 1? How many of the observations were positive versus how many were negative? I mean, we can, for example, for variable 1, they have the sign of the income forecast error, the sign of the unexpected earnings. 1,231 of the firm month announcements were positive in their sample, and 1,109 were negative using variable 1 net income. So we could answer that, right? We could find size of just basically find where's firm API overall. How many of these observations are positive? So we could do sum of 1 equals firm API overall, all rows, column 2. 924 were positive, and sum negative 1 equals firm underscore API overall, all rows, column 2. 779 were negative. So we can do 779 divided by, what was this, 924? Divided by 924. So 84% of the observations of the or wait a minute, 924 plus 779 is 1703. So 994 divided by 1703, 58% were positive. 774 divided by 1703, 45% were negative, or 779, sorry, divided by 1703. Anyway, and just see, is that similar to theirs? Their total is 1231 plus 1109. So 1231 divided by 2304. I mean, it's comparable, and so forth and so on. So we could replicate table 6. Not going to replicate that. But we are going to replicate in the next video. This section, the value of annual net income relative to other sources of information. They compute a couple of metrics that sort of indirectly assess the value of annual net income. They compute this right here. We're going to compute this for our sample. And then they compute, and for their sample, the total information in net income was 0.731. Averaged over all firms in years. So we're going to compute that same thing to see what we get. And then what's the value of net information concerning the average firm? Which is this formula for, and they got a sum of 0.165. And then they computed the income information. N1 is the number of occasions on which the income forecast error was positive, and N2 is the number of observations where the income forecast error was negative. And then they've computed the income information, and they got 0.081 for variable 1 and 0.083 for variable 2. And then they made this conclusion here. About 75% of the value of all information appears to be offsetting, which in turn implies that about 25% persists. And of the 25% which persists, about half can be associated with the information contained in reported income, which gives some measure of the value of net income. How much information is it capturing? And we're going to see if we get similar numbers to these numbers in our particular sample time period, and we actually will. So that's what we'll be doing in the next video. So I hope you enjoyed this video. I know it was a little it gets a little complicated, and maybe I'm not doing the best job of explaining what I'm doing, but you have the video, you can pause it, you can see the code I typed, and you can wrestle with things on your own, which is what you're supposed to be doing anyway. At least I give you the code, and you know what to, so you know the right way to do it, and you can go and wrestle with each block of code like I did, especially in here. You can say, why did he actually do that? I explained why, big picture why, but I didn't explain every little thing, because that's for you to wrestle with, and you'll see exactly why I did it once you see what the code does. You can apply that, and that's how you'll learn. And this video series is directed towards students who don't just want some easy little, it's not like here's a solution. They don't just want an answer key. They want to learn how to code. They want to learn. And so for the students who are seeking to learn, they will find these videos helpful. And those that aren't really seeking to learn, just trying to find answers to questions that they don't really want to go learn themselves, they won't find these videos very helpful, which is I'm not targeting those individuals. But I hope you enjoyed this video, and I'll see you on the next one. Let me know in the comments or via email. Well, you can let me know in the comments if you want my email address, first of all, and I'll send it to you in a private message. And you can reach out to me, and we can talk if you need more help regarding what I'm doing in the video.